back. Today we're doing problem 103, binary tree zigzag level order traversal. This problem is really similar to binary tree level order traversal. It's another Leetcode problem. I'll post the link in the description below. But let's read the description. Given the root of a tree, return the zigzag level order traversal. So left to right, then right to left for each level alternating in between. For the first example, the output's a list of lists. It goes 3, 20, then 9, because it goes right to left in the second level, back to left to right, 15 to 7 on the third level. So this problem is same approach as level order traversal. We're going to do a BFS at each level and use a queue to get the nodes at each level. Then that still hasn't solved the zigzag order, right? Whether we have to go left to right or right to left. But it's actually pretty simple. We'll just use a flag to let us know. It will indicate what order we want to go in. If we're going left to right, don't do anything, just append it to our global result that has all of the levels. If we're going right to left, then we'll just reverse the list and then we'll append it, right? So let's get started. Let's create our result empty list. If our root is null, we'll just return an empty list. Let's create our queue and then add our root into it while the length of the queue is greater than 0. Let's say size is equal to the length of the queue, and then let's say current level is equal to nothing. It's just an empty thing, right? And then for I in range size, we're going to iterate through every node that we currently have within our queue. Our current node is equal to queue.pop in the front. And then now we're going to append that node into our current level. But not the node, we're going to append the value. Here, at this point, we can check if it has children. If it does, let's add it to the queue, right? Same with the right children. And at this point, once we get down here, we can append our current list, which has all of the nodes at the current level. Into our result. And finally, we can return our result. So if we run this, we see here that it's wrong because we still haven't taken on the problem of zigzagging, right? We just have a level order traversal. But I think it's good here to show that, hey, BFS will get you just the level order traversal. Now I think it'll make more sense once we reverse level by level how that's going to work. We see here on line 27, that's where we're actually appending into our result. So before that, let's do some check to see if we should reverse the list before we append. So let's create some left to right equals true. This flag is going to let us know whether we should go left to right or right to left. So before we append, maybe right here, if left to right is true, we'll just set left to right equal to false, so that the next time it will go into this case. If it's false, let's set it to true. Well, before we do that, if it's false, that means we're going right to left. If we're going right to left, well, that means that we have to reverse our list. After we reverse our list, we'd have to go back and set it back to true again, right? Then we can append to our result. And then when this all finishes, we'll just return the result again. So let's run this. Great. Let's see if this works when we submit it. It should. Nice. So this problem, runtime wise, it's just doing a BFS. So runtime of BFS is big O of vertices and edges. So we're exploring everything in this tree. So you can kind of treat that as like an O of N, because it's just going through all of the connections in the actual tree. So every node is visited, and then we also maintain the entire tree in our result, right? And we're using this queue, so that's also O of N. And that should be it. Very nice.